Hello, my name is Selvarajan, and I'm going to deliver a speech on a study on Turing machine and its applications. So first, let us see what a Turing machine is. Turing machines are a fundamental concept in the theory of computation and play an important role in the field of computer science. They were first described by the mathematician and computer scientist Alan Turing in 1936 and provide a mathematical model of a simple abstract computer. In the context of automata theory and the theory of computation, Turing machines are used to study the properties of algorithms and to determine what problems can and cannot be solved by computers. They provide a way to model the behavior of algorithms and to analyze their computational complexity, which is the amount of time and memory they require to solve a problem. A Turing machine is a finite automaton that can read, write, and erase symbols on an infinitely long tape. The tape is divided into squares, and each square contains a symbol, and each square is also called as a cell. The Turing machine can read only one symbol at a time, and it uses a set of rules, also known as a transition function, to determine its next action based on the current state and the symbol it is reading. The Turing machine's behavior is determined by a finite state machine, which consists of a finite set of states, a transition function that defines the actions to be taken based on the current state and the symbol being read, and a set of start and accept states. Turing machine was invented by Alan Turing in 1936, and it is used to accept recursive enumerable languages. They are languages generated by type 0 grammar. The Turing machine begins in the start state and performs the action specified by the transition function until it reaches an accept or reject state. If it reaches an accept state, the computation is considered successful. If it reaches a reject state, the computation is considered unsuccessful. Turing machines are an important tool for studying the limits of computation and for understanding the foundations of computer science. They provide a simple yet powerful model of computation that has been widely used in research and has had a profound impact on our understanding of algorithms and computation. So, let us see who invented the Turing machine. As the name suggests, it is Alan Turing who invented the Turing machine in 1936 while studying for his PhD at Princeton University. The English mathematician Alan Turing published a paper on computable numbers with an application to the Einstein's problem, which became the foundation of computer science. In it, Turing presented a theoretical machine that could solve any problem that could be described by simple instructions encoded on a paper tape. One Turing machine could calculate square roots, whilst another might solve Sudoku puzzles. The applications of Turing machine was limited. Turing demonstrated you could construct a single universal machine that could simulate any Turing machine, one machine solving any problem, performing any task for which a program could be written. Does it sound familiar? He had basically invented the computer. So let us see how a Turing machine works. A Turing machine consists of an infinitely long tape, which has been divided up into cells, and each cell can contain either 1 or 0 or an empty space. Above one cell of the tape is a head, which can either move left or right and can read the symbols written in the cells. The head is also capable of erasing symbols and writing new symbols into the cells. The direction that the head moves, which value it erases, and which value it enters are dependent on a set of instructions provided to the machine. So, a Turing machine can be expressed as a 7-tuple, consisting of Q, T, beta, summation, delta, Q naught, and F. So let us see what these symbols mean. So the first symbol is Q, which represents a finite set of states consisting in the Turing machine. T is a tape alphabet, symbols which can be written on tape, such as 0, 1, X, Y, and many more. B is a blank symbol, and every cell is filled with B except input alphabet initially. Summation is the input alphabet, symbols which are part of the input alphabet. Delta is a transition function which maps Q cross T to Q cross T cross L, R. Depending on its present state and present state tape alphabet pointed by head pointer, it will also move to new state, change the tape symbol, and move head pointer to either left or right. Q naught is the initial state, and F is a set of final states. If any state of F is reached, input string is accepted. These symbols can be visualized in the diagram shown below, where the head is moving left or right, read and write on the infinitely long tape. So let us see an example of a basic Turing machine for the language which accepts equal number of 0 and 1, such that the number of 0 or 1 is greater than or equal to 1. Such a language can be represented in a simple format such as L equal to 0 power n, 1 power n, such that n is greater than or equal to 1. For such a Turing machine, the value of Q, the finite set of states, would be Q0, Q1, Q2, Q3, where Q0 is the initial state, and T will be 0, 1, X, Y, B, where B represents blank. The summation is 0 and 1, and F is a set of finite states, where a final state is Q3 in this machine. A transition function delta is given in the below table, where the rows are the finite set of states and the columns are the symbols which can be entered in the infinitely long tape. The transition function shows where for the head pointer to move when it encounters a row which is a finite state and a symbol on the infinitely long tape. For example, let us see the cell where Q0 and 0 meet. It shows that Q1, X, R, which means that the head pointer should move to Q1 and convert the 0 to an X and move towards the right. For the same row, let us see Q0 meeting Y. If Q0 meets Y and the head pointer reads Y in Q0, it should move to Q3, change the current Y to Y, which means leave it as it is, and move to the right, which means the head pointer should move to the right. Similarly, let us see what will happen if Q1 when head pointer is in the Q1 state and it reads 1. It denotes that the head pointer should move to its left, convert 1 to Y, and in the data flow, it should be presented that the flow is in Q2. Similarly, let us see when Q3 meets a blank space, such as B. It is denoted the halt, which means the language is accepted. So this is a basic transition function for a simple Turing machine. So let us see the equivalence of a Turing machine. A Turing machine can be considered as a push-down automata or PDA with additional stack, or it can be considered as a finite automaton with 2 stacks. Their applications are unlimited, limitless. So let us see the applications of Turing machine. The applications of Turing machine, as we discussed, are limitless. But for now, let us see few important applications used in the world. First one being, it is used to solve any recursively enumerable problem. It is used for understanding complexity theory. It is used for implementation of neural networks which is an important application in the current world, in the evolving AI world. Next, it is used for implementation of robotics applications, which is also an in-demand application considering the shift of world towards robotics. Next, Turing machines are also used for the implementation of artificial intelligence, which again is an in-demand application considering the world moving towards artificial intelligence rapidly. It is also used as a theoretical model to analyze the time and space complexity of algorithms. This application has been in demand from a very long time and will also be in demand for a very long time indeed, considering the new and updated algorithms and their required proofs. Next, they're used in computational biology to model and analyze biological systems. This application is widely renowned and has a lot of limitless applications in the real world for considering new biological systems. It is also used in artificial intelligence as a model for learning and decision making. It is also used to study the relationship between classical computing and quantum computing. This demand will increase in the future for this application as there's a shift from classical computing to quantum computing rapidly. And as we move towards quantum computing, this application of Turing machine will increase in demand. And that is the end of a study on Turing machine and its applications. Thank you.